Welcome back, Falcons. We are moving into part 2 of chapter 11, all about understanding randomness. So, last time we finished up talking about how to use our calculator. And in this case, we are going to actually walk through a couple different example problems. I'll show you again how to use your calculator, and then we will move forward. First example. Suppose that 30% of the subscribers to a cable television service watch the home shopping channel at least once a week. You are to design a simulation to estimate the probability that none of 5 randomly selected subscribers watches the shopping channel at least once a week. So, no, 30% of the subscribers watch the channel, 70% of the subscribers don't watch the channel. If we are understanding those are the different types of outcomes, we are selecting 5 subscribers at random, and we are seeing, do they watch the channel or not? So on the next page, we're going to go through the possible options. But if we have 30% for one group and 70% of another group, I want you to think of how could we devise our numbers and think I have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. That's 10 total numbers. Believe it or not, that's 10. I can split these even percentages and say, if I was designing this, let's say 0, 1, and 2 are watchers. And then 4, 5, 6, 7, 9 are non-watchers. If we were going to run a simulation, what we would do is we look at a random number generator or a random number list that is provided to us, or we'd use our calculator and get a random number. And what we're going to do is select 5 of these. And so we're looking at a string of numbers to see 5 randomly selected subscribers watches the channel at least once. Which of the following statements of digits would be appropriate for modeling individual subscribers' behavior in this simulation? So we walked through what the model would look like. Let's see if this was like a multiple choice. Which of the following assignments would be appropriate for modeling the individual subscribers' behavior in this simulation? Let's look at the first one. 0, 1, 2, and 3, watch. So that's 4. 4, 5, 6, 7, 8, 9. That's 6, don't watch. That's 40% to 60%. That doesn't match what we want. It's close, but it doesn't match. Assign 1, 2, 3, 4, 5 is watching, and then 6, 7, 8, 9, 0 is not watching. That's a 50-50 distribution. Again, that is not what we want. Assign 0 as watching the channel at least once a week, and then 1, 2, 3, 4, 5. So that would be 1/6 or 16% to 5/6, which is what, 84%? Not watching. Again, that is not what we want. It's close, but it's not what we want. So each one of these, if you notice, is not quite what we want in the picture. There's got to be another way. The closest one is A, but it's not A. In fact, none of these options are good, even though one of them is highlighted in yellow. The idea behind creating a simulation, and really the best way to demonstrate this Monte Carlo simulation, is to do one. So we will practice more than one before you take the test, obviously. The idea is using random numbers, simulate the outcomes of a tennis game between Bill and Mike, with the additional condition that Bill is twice as good as Mike. So what does it mean to be twice as good as someone? Well, that means that if I played 3 games, Bill would win 2 and Mike would win 1. Or the ratio is 2 to 1 for Bill to Mike. So what we need to do, first, list all possible outcomes of the experiment. So either Bill wins or Mike wins. Those are the 2 options. Next, we're going to determine the probability of each outcome. Well, Bill is twice as likely to win, so that would be 2 out of 3 versus Mike's 1 out of 3. And since Bill is twice as good as Mike, he will win approximately 2 games for every one Mike wins. Hence, the probability is 2/3 to 1/3. We can think in ratios, we can think in probabilities, we can think in fractions. Next, we're going to set up a correspondence between the outcomes of the experiment and the numbers. So the random digits, 1 through 6, can be used to represent Bill's wins. 1, 2, 3, 4, 5, 6, that is 6 digits. The random digits 7, 8, and 9 can be used to represent Mike's wins. And if we see a 0, we're just going to ignore that because we want 2 to 1 or 6 to 3. All of those are equally likely. So then I'm going to ask you guys, list out what are the numbers you're using and who gets what determination. So in our list, we're saying we'll use the numbers 0 to 9. 1 through 6 is Bill wins. 7 through 9 is Mike wins. The digit 0 is disregarded. Now we describe how does a trial end. So a trial ends when 6 games are won. We record the outcome of the set. So once we record that outcome, we're going to tabulate and average those at the end. And this time, we're going to use a random number table. So let's look through here, and we're just going to go left to right. So starting with our first one, remember 6, 1, 2, 3, 4, 5, 6 are Bill wins. 7, 8, 9 are Mike wins. So we have Bill, 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 disregard. 1, 2, 3, 4, 5, 6. Bill won the first 6 games. Trial stops when 6 games are won. So it took 6 games for Bill to win all 6. So look at the next set of numbers. 4, 1, Mike wins. Mike wins. Bill, Bill. So we have 1, 2, 3, 4, 5, 6. So this time, there's our second break. Does this pattern make sense that we saw 6 wins for Bill, Mike in this time, and how many games do we have? 1, 2, 3, 4, 5, 6, 7, 8. 8 games, he won 6 of them. So that would be 6 out of 8. In the first one, it was 6 out of 6. So by using this random number table, or random number integers from a table, is how you would conduct the experiment. In the real world of simulations, we would randomly choose a starting place. On the test, we will always start in the upper left-hand corner, which is how I exemplified it. So if we randomly started in a different spot, you can see why it's important to randomize this. Let's say we started at this 7 position. We have Mike, Mike, Mike. Bill, ignore. Bill, Mike, Bill, 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 Bill. So this is once Bill wins 6 to 4. How many times do we want to repeat this trial? Well, we said we wanted to record it 3 times, like a tennis match. So a set is complete when a player wins 6 games with a margin of victory of 2 games. This is how tennis works, actually. A match is winning 3 of 5 sets. So outcomes, Bill wins or Mike wins. Those are outcomes. Once we have 6 wins, then we freeze it. That's 1 set. Repeat the experiment or trial and tally the outcomes. And so what we're doing is we compute any statistics and state the conclusion. So if we started at the 7, the first one is 6 to 4, Bill. The second set is 6 to 3, Bill. And the third set is 6 to 4, Bill. So this gives us our conclusion of our tennis match between Bill and Mike. Now, that's not the only way that we can run these types of simulations. You also can use your calculator. So if we wanted to use our random number integer calculation on your TI Inspire, TI-84, you can hit Math, Probability, then go to Random Int, and we want 3 numbers. We want 2 to 1. So let's just use 0, 1, and 2. On my TI Inspire, I go to Menu, Probability, Random, and then I want Random Integer. And so what we can do is say 0, 2, And this will just give me a random number between 0, 1, and 2. So let's say, well, what goes with what? I'm going to say 0 and 1 are Bill wins. 2 is a Mike win. Now notice, I have to tell you how the game actually runs so that I can interpret what these numbers are coming up with. So if I hit enter, I see 1. So that's one game for Bill. 2 games for Bill. 3 games for Bill. 4 games for Bill. 5 games for Bill. 6 games for Bill. So he won 6-0. The next time, 1 to 1, 2 to 1, 3 to 1, 4 to 1, 5 to 1, 6 to 1. We can see that we're getting these random numbers. If we switch back to the notes, we can see after each time we hit enter, we start tabulating these zeros, 2s, and 1s. Your answer is going to be different than my answer because these are randomized. So it's about listing out the process rather than getting the exact match. So how do we equalize everything? Well, we would average the total amount of games played. So with a simulation experiment consists of several trials. In the previous one, it was until we won 6 games. That was a trial. Each trial consists of 1 or more components. What do the numbers go to for the outcomes? In a simulation, a trial can be a fixed number of components. So in this case, who wins 6? Or a varying number of components. How many times till I get 6? Depending on what we wish to record. In the tennis simulation, each trial ended when we had 6 wins. Each trial, or a set in tennis, was a varying number of components, the games won. We may wish to record the number of games required to win 6. If we do this repeatedly, we can find an estimate of the length of a set by averaging. So a fixed length trial would consist of every trial being the same number of components. Okay, for example, suppose McCart's farm is an egg farm. The McCarts raise chickens for their eggs and have a hen house with 10 nests. Because they have been collecting eggs for some time, they have found that each hen will lay from as many as 0 to 2 eggs. Based on past experience, they estimate there will be no eggs about 10% of the nests, 1 egg in 30% of the nests, and 2 eggs in the remaining 60% of the eggs. The idea is we want to conduct a simulation to estimate how many eggs McCart will collect on each visit to the hen house. So they're seeing each nest 2, 3, 4, 6, 7, 8, 9, 10. There's 10 nests. So our trial is going through 10. And we should think these will add up to 100%. So 0 eggs, how do we want to establish it? It said 10%. So let's call the number 0 for 0 eggs. For 1 egg, we see that it was 30%. So let's say 1, 2, and 3 would correspond to 1 egg. And then 2 eggs, that would be 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6. 6 for 60%. Our total is 100, or 10 digits that we're using. And we're going to run a simulation of 10 numbers. So we list out all the possible outcomes of the experiment: 0, 1, or 2 eggs. We determine the probability of each outcome. 0 happens 10% of the time. We were given that. 1 egg happens 30%. 2 eggs happens 60%. We assign the values, which we did before. A trial ends with 10 nests. So once we get 10, we're done. How do we get that on our calculators? Because we could either look at a random number table, which I have here, or I can say menu, probability, random integer, and I want 0 to 9, and I want to do this 10 times. If I hit enter, this would be one full trial. I have 0, 8, 2, 6, 0, 0, 8, 2, 7, 5. And then I would tabulate how many eggs I would get. So 0, we said, was 0 eggs. 8 is 2 eggs. So I have 0 plus 2 plus 1 plus 2 plus 0 plus 0 plus 2 plus 1 plus 2 plus 1. Once I figure out those allocations, I want to run this 4 times. So I'll go up and hit random int 0 to 9, do it again. Do it again. And then I'll do it again. So now I have 4 trials. And based on the 4 trials, we can then see how many eggs we get in each trial. If we're able to calculate how many eggs happened in each trial, and we had 4 of them, all we need to do is average the total number of eggs divided by 4. And this would allow us to estimate from our simulation as opposed to going out to the chicken coop every day and collecting the eggs. You can see why simulation is so useful for allowing us to figure out if we need to get more chickens to collect more eggs. So to summarize, a simulation experiment consists of several trials. A trial usually consists of several components. We record the outcome of a trial. A trial can be fixed. We record the number of components required to satisfy some criterion, or a trial can be of varying length, ending when a condition is satisfied. We record the number of attempts to complete the trial. So think number of free throws required to make 10, or the number of trials to complete some criterion, win the match. Last example. Suppose a cereal manufacturer puts pictures of athletes on cards in the boxes of cereal. The pictures are Tiger Woods, Serena Williams, David Beckham, and the manufacturer claims that 20% of the boxes contain Tiger Woods, 30% are going to be David Beckham, and the rest are Serena Williams. We want all 3 pictures. So how many boxes of cereal do you expect to need to purchase to obtain all the athletes? I want to figure out how many times do I have to go to the store and buy a box of cereal until I get all of them. So we are going to simulate that. So first off, the goal, we want all 3 pictures. The outcome is Tiger, David Beckham, and then Serena. How many boxes of cereal do you expect to need to purchase to obtain all 3 athletes? So what we're going to do is we're given those percentages. 20% are Tiger Woods, 30% are David Beckham, and the rest, 50%, is Serena Williams. Here, we're going to assign our numbers then. So 20%, or 2 numbers, will go to Tiger. 30%, or 3 numbers, would go to Beckham. And 5 numbers would go to Serena. The trial ends when we've collected all 3 cards, or we've got a 0 or a 1, a 2, 3 or 4, and a 5, 6, 7, 8, or 9. Record the number of boxes it took to purchase. Note that each trial is of differing length because we're seeing how long it will take to get up to all 3, not just buying 3 boxes. So if we look at our random numbers that we are provided with, notice the color that I used to make this helpful. 6, 1, 4. 3 boxes. That's all it took. Now we have 2, 4, 2, 0, 4, 1, 9. 4, 5, 6, it took 7 boxes to get all 3. The next one, 8, 6, 5, 4, 6, 0. 6, it took 6 boxes. How many trials can I run in this list of random numbers? About 14. So what do I need to do? I need to organize my outcomes with the number of trials that I went. So the trial 1, it took me 3 times. I bought 3 boxes before I got all 3. The second was 7. The third trial took me 6 boxes. 7, 8, 11, 5, 3, 16, 7, 3, 6. You can see that we are counting up how many boxes it took to purchase before I got all 3 of them. Well then, how do I find the expected value? Well, the expected value is to add up all of the boxes and divide by 24. We will get much more into expected value later, but literally it's just the average. We've done this before. So with a simulation of 24 trials, we can now calculate an expected number of boxes you'll need to purchase by adding up all of the number of boxes it took before we got all 3, dividing by the total number of trials that we ran. So I would get 151 divided by 24. which is 6.29. Keep the average. Don't round. You can expect to buy about 6 to 7 boxes to get all 3 athletes. So a quick note before we finish on how to answer. Note that the way the question is worded indicates how you should respond. The previous example asked how many you would expect to buy. That suggests a mean or an average. Had we been asked how many will you have to buy to ensure that you get all 3 cards, we would probably respond with the maximum number we found and respond with, we may need to purchase 16 boxes to be certain of obtaining all 3 cards. Now, where does 16 come from? Well, if you look at our trials, the longest it took for us to get all 3 was 16. So in order to ensure from our simulation that we get all 3, we would have to buy the maximum number. I have one more example for you to design an experiment. And I may ask you to actually share this in class. Suppose that at Divine Child, so at DC, 150 students have parking passes. Also, let us suppose that the student council holds a golden permit lottery each month to select 2 students to get reserved parking next to the entrance. So you get the first parking spot right next to the entrance. Last month, 2 students from student council got the winning permits. Other students in the school assumed that the fix was in. If 32 students are in student council, if 32 students in student council have parking permits, is it unreasonable to think 2 students from student council would get the ticket in a fair lottery? So think through this, because then we could run a simulation to see how unlikely this is. We have 150 students have parking permits. 32 are in student council. If 2 students from student council get the tickets, is that fair? That's the question. So how do we design and run a simulation to determine if this is plausible? So what are the components? We're drawing a parking permit, and either they're in student council or they're not in student council. The probability of someone being selected at random of being in student council is 32 out of 150, which means that the probability that it's just a regular student, not in student council, would be 118 out of 150. Now we've determined our probabilities. So what should we do? Well, we will randomly generate 2 numbers from 1 to 150 to model the lottery. Now, if I'm dealing with a 3-digit number, I should have 000 through 999. So we're just going to pick 2. It's a fixed trial. That would be 1 trial. We're going to assign numbers 1 through 32 to student council and assign 33 to 150 to the rest of the parking permit holders. If we were to use a random number table, what we would do is say we're going to use 000 through 99999. We're going to skip 000, and the way we're going to partition this is 001 to 192 would be student council. 193 to 900 would be non-student council, and we're just going to omit the last 100. If you want to see why, I can explain this further. Then we just run a simulation. We're going to do this 50 times to find the number of times both winners are from student council. What you have to do then is run this simulation and keep track. Are the 2 people in student council? So clearly, I ran 10 trials in front of you to find the number of times both winners are from student council. Just running the 10 trials I ran, I would expect both winners of the lottery to be from student council about 1 out of every 10 drawings, because in this one drawing, I got 17 and 1. Those numbers work. That suggests that we can expect both winners to be from student council about once a year, which is not that surprising. So even though it doesn't seem fair, it is plausible. So it's not rigged. And that's the trick. people misunderstand statistics because we're bad at probabilities. We don't understand that likelihood is actually built in to the randomness of things. We'll get into much more detail of that when we get to Unit 4, but I want to put a pause on this right here. Thank you for your time, Falcons. This is the end of Chapter 11. I will see you in Chapter 12 when we talk about sampling techniques.